Hello and welcome to Fouraye Education. Today I'll be teaching financial mathematics. In this section, I want to outline the concepts of Brownian motion and the ideas underlying the concept of Brownian motion. Now, we saw a couple ideas previously, such as expectation, conditional expectation, martingales, and stochastic processes. These will come in handy when looking at Brownian motion. Now imagine stock movements. How do stocks move? They move apparently randomly. They can have different paths in time. Now say we want to model a stock in the future. It can go up, maybe down, then up again, and down and up. Basically, random movement. We can have many different paths, as you can see. These are generally computer generated when it comes to how we usually look at them in real applications. Well, these are three different paths, right? And they're apparently random. How do we model these paths mathematically? How can we model stock movement mathematically? So we can't just write a function which moves similarly to a stock. So how we approach this is that we look at symmetric random walks first. Symmetric random walks are a more discrete version of this with a couple limitations. Now, symmetric random walks are or they can be shown like this, right? So they move very discretely, as you can see. They don't move like a stock price. But we can maybe build something out of this to get our stock price path. So as we can see, the first limitation is that it's negative. The second limitation is that it's not exactly continuous, as in it's discrete, right? So we have these values over here. It's very discrete and it's not very zigzaggy. We can make it more zigzaggy. First, let's define symmetric random walks. Symmetric random walks, also known as drunk walks, since when you're drunk you walk zigzaggy, can be shown in terms of a stochastic process. They are a stochastic process. The symmetric random walks are a stochastic process generated through the toss of a fair coin. So we can define a random variable xi such that it gives us 1 if we roll heads, negative 1 if we roll tails, and then the general random walk, which I'll denote as r for random, well, let's say r up until a point t, big T, is going to be the summation from 0 to t of the random variable, right? Let's say j to avoid confusion. So yeah, we just sum these up. Also at 0 it's 0 since it's the initial start point. Now there's some noteworthy things, is that, well, first of all, the expectation of the increment will be 0. And how we show the increment is basically r, say, t plus 1 minus rt. The expectation of the increment will be 0 because it can move down by 1 or up by 1. Basically 0. 0 or 2 is 0. Yeah. Let's try drawing one of these random walks. How do they look like? Let's say till time 5. So if you roll heads, it goes up. If you roll heads again, it goes up again. If you roll heads again, it goes up again. Maybe at time 3 we roll tails and it goes to here in time 4, then heads again. Another path could be, well, heads, and let's say tails, heads, and then tails. Another path could be tails, heads, tails, heads. And different paths can be modeled off this stochastic process. But it's important to look at some very important properties which will be applied to Brownian motion later on. So let's look at first one. So the first thing is that, well, the increments are going to be independent. So what I mean by that is that the increments will not depend on our knowledge at a certain time. Basically, say the increment wt minus 1 minus wt minus 1 will not be dependent of our knowledge at wt minus 1, because even if, let's say, if the stock price is 50 now, will the path depend later on whether it goes up or down? Will it depend on the current stock price? No, it's random. So the increments are independent. The next property is a very, very important property. It's that symmetric random walk is a martingale. But before this, I'll just give some simple properties. So the expectation is 0, the variance is 1, the expectation of the increment is 0, and the variance of the increment will be, well, the times let's say it's like the time is t minus 1, the other one is t minus 2. It'll give the difference between the times for the variance, for the increment, of course. So anyways, on to our main property. The symmetric random walks are a martingale. Now, how do we show that they are martingale? Let's say that the expectation of a random walk R at a given time t with condition to a given time s. Now this normally has to be equal to R of s if it's a martingale, right? So how do we show that it's equal to R of s? First of all, we say RT plus RS minus RS. This little trick here we use a lot in stochastic calculus. So we then group these two together as the increment, and then we take this out by the property of linearity. So we can then say E of RT minus RS conditioned to f of s plus E of RS conditioned to f of s. Now this on itself is going to be R of s because we already know s. Now this, due to the reason that the increments are independent, will not be dependent to this, So it can be stated as a normal expectation of the increment. And we know that the expectation of the increment is 0. So it's 0 plus r of s, which is rs. Hence, symmetric random walks are a martingale. Now, another very important concept which we must look at along with the symmetric random walk in order to understand Brownian motion is the concept of quadratic variation. Quadratic variation will be a very important concept because it comes in at all points of Ito calculus. In the case of Ito's formula, as well as the Ito integral, we'll see quadratic variation. Now, quadratic variation, or the second variation, can be shown as m, and then let's say t is going to be equal to t j equals 1 mj plus 1 minus mj squared, or mj minus 1. Squaring. So yeah, as you can see, quadratic variation comes from square. So this is basically the quadratic variation is basically the sum to a certain t value of the increments squared. Now, the quadratic variation for the random walks in this case is t. And we'll look at the quadratic variation for a Brownian motion too later on. So now, to move from random walks to Brownian motion, we have to look at scaled random walks, right? Scaled random walks. We want the random walk to move a lot more. So we'll use scaled random walks. So scaled random walks are an approximation to Brownian motion, shown in the form of this. And it's equal to this, r being again the random walk, right? And this portion has to be an integer. And when we partition this, we can see, let's say, t is in the middle, right? And we have k, we have p. This value, p, which is between two values which are integers, can be approximated. And so, as well, yeah, it can be approximated. And well, since it's integers, the values between these t's aren't really there for us, and they're not really continuous, so we can't really look at it in a Brownian motion way. So we have to, in fact, make it so that n tends infinity, so that there are little portions, and it goes, well, towards a Brownian motion. Now, the Brownian motion, which we always talk about, is that random movement similar to a stock. Of course, Brownian motions can be, well, negative, while stocks can't, but Brownian motions will look like the stock movements, so yeah. the initial zigzagging shown is, well, similar to what a Brownian motion would be. Now, a Brownian motion. A Brownian motion is a stochastic process. Let's give ourselves a space, sigma algebra, and measure, yeah? So, a Brownian motion, generally denoted using a W, and say t is bigger than or equal to 1, is called a Brownian motion for any time points between, say, 0 and big T, right? And the increments are independent and they tend a normal distribution. So the thing with Brownian motion is that the increments of the Brownian motion itself are random variables. So Wt minus Wt minus 1, well, t plus 1 because t can be 0. So Wt plus 1 minus Wt are random variables on themselves. So Wt minus W0, right? W1, sorry. W2 minus W1, W3 minus W2. These are all random variables. And these random variables tend toward a normal distribution, or are normally distributed. And their mean are, as shown before with random walk, 0. And their, well, what do you call it? Their their time point is going to be t plus 1 minus t. Their variance, right? Yeah. Or should I say, like, instead of using this, say time 0, right? We'll use this notation instead. So using this notation, we can say that ti minus 1 minus ti. Anyways, I changed the notation so you might not really get it, so I'll write it entirely from beginning. So say ti plus 1 minus ti is going to tend a normal distribution. Ti plus 1 minus ti. Okay, so this is the condition for a Brownian motion. Now, what are the properties of a Brownian motion? The properties of a Brownian motion are as follows. First of all, let's say we have a filtration which is associated with the Brownian motion, right? So we have these two. First of all, any future time filtration has to be a member of the past filtration. So what I mean by that is that f of s has to be a subset of f of t. Well, yeah, now. Other than that, the Brownian motion has to be adapted to the filtration. And other than that, the increment is going to be independent of the filtration, or is going to be independent of the knowledge at time t, which is previous to that increment's information. So we'll use this again. Say s, right? S minus WT is independent of FT. Now, with all of these, we can say that the Brownian motion is a martingale. This is the martingale property of the Brownian motion. So let's look at it. The conditional expectation of the Brownian motion at time t conditional to a filtration S is going to be W at S, and we can find this using a very similar trick to previous computations as such. So yeah, we take this out through linearity, and this will not depend on this because increments are independent and we already know the information at time S, so this will simply come out as Ws plus the expected value of this, and this is simply 0, so it's just Ws, and that's the proof that Brownian motion is a martingale. So now that we know this, let's look at some special martingales containing Brownian motion. I'd like to bring our attention to two very important ones, right? First of all, the exponential martingale. The exponential martingale can be given as such, usually denoted using z. It's going to be the exponential function of sigma Brownian motion minus 1 over 2 sigma squared t, where sigma is bigger than 0 and sigma is volatility, or standard deviation, both same thing. So this is a martingale. Now comes the rigorous proof for it. So zt is equal to exponential function of sigma wt minus 1 over 2 sigma squared t, where sigma is bigger than 0. So let's say, right, we have the expected value of zt conditioned to fs. So we have the expected value of the expression above, right? So if you realize this is random because of this, so what we're going to do is use a very similar trick which we use in previous things, where we do this basically. Sigma of wt minus ws times the exponential function of sigma ws minus 1 over 2 sigma squared t. Then we'll say conditional to fs. Now we can use the property of taking out what's known and take this out, and then we can say that this is an increment, so it doesn't depend on this. So we can simply rewrite this in a more simpler form as such. So yeah. Now, what we want to do is show that this is equal to zs. So to do that, we have to actually compute this expectation over here. Now this expectation is very hard to compute, so I'll just give the answer, which is the exponential function of 1 over 2 sigma squared t minus s. So now we have this and we have this. We can see that this cancels out with this, and then we have this, which gives s z of s, which shows that the exponential martingale is indeed a martingale. And another very useful one, which we'll talk about, is this. This is also a martingale. So for its proof, we'll just say z again, right, is going to be equal to e of this, constraint to fs minus t, and then this will open as vt minus vs plus vs squared expectation conditional to fs. Then we'll say that, well, we'll take this separately, and then we'll say we'll complete it so that it's mathematically true. Now wt minus ws expectation comes as 0, so this part is gone, and this is simply w squared s. And so what we end up with, and also this is the variance, so we'll just have t minus s for this, so we'll have t minus s plus w squared s minus t equals e of zt conditional to fs. And t's cancel out. This is z of s. Again, we've proven that this is a martingale. And that's basically it for what I want to talk about regarding Brownian motion. Thank you for listening, and I hope you like and subscribe.